I'm Dave Brown from National Center for Atmospheric Research, and I'm going to talk about how this is kind of a case study of using Python to solve a specific big data problem that was faced by, that is still faced by climate modelers at NCAR. And this is based on this talk is based on past and ongoing work that's primarily led by some of the people on listed below my name here, and I'd like to thank them up front. So here's my outline. First I'll describe the problem, and then I'll talk about the test scenario that came to be called the time slice to time series bake-off. I'll explain that in a while, and then I'll talk about how there was a simple, pretty simple Python-based solution that beat the other contestants in the bake-off. And after that, I'll talk a little bit about PyNIO, which is a package that we developed at NCAR based on the NCL IO library. If you haven't heard of that before, it's a multi-format data IO library package. It uses the NetCDF data model, and it allows access in a NetCDF-like way to a number of data formats that are used by atmospheric and geoscience practitioners. So it interfaces with NumPy, and I'll talk about it more later. And then I'll end with just talking about what our plans are for the future. So just first of all, just a little bit about climate data. So, the climate models generate lots of data. They're going hundreds and thousands of years. And so usually the data is, there's hundreds of variables, and they're 2D and 3D mainly. So, for 1 degree grid, you'd have 180 lats by 360 longitudes. And if it's 3D, then you'll also have levels, which could be either atmospheric levels or ocean levels. And that's probably enough to say about that. So just for example, NCAR's one of its big things is contributing to the IPCC analysis and assessment reports, and that's through the CMIP project, which is the Coupled Model Intercomparison project. And so, for the previous CMIP project, NCAR produced about 120 terabytes of data through its CESM3 model, and about 10 terabytes was archived in the archive. For CMIP5, that increased to 1.2 petabytes of data. That was the raw data, and a mandate for CMIP5 was that all this data, which in raw form is just one time step, and all the variables, it had to be converted to time slices, which means one variable and a time series type file. So that the numbers here in red are an indication of NCAR's problem. Basically, there was 1.2 petabytes of raw data, and in the time that was available, only 760 terabytes was converted to the time slice format. So, and that's like 15 months or so that they had to do it, something like that. Just to say that the reason for it converting to time slice is it's much easier for a scientist to use it. The raw model output is very inconvenient because you have to paste things together, and you don't necessarily want to talk about, aren't interested in all the variables that are in the data files. So really what you want to do is transpose the data into files that contain one variable with a lot of time steps, and 10 years or so, some convenient quantity. And here's just a diagram that kind of illustrates what needs to happen. So you've got these files with many variables, and you want to convert them into files with one variable. So pretty straightforward, really. So since NCAR was having such a problem doing this, we organized this time slice to time series bake-off just to try to figure out what might be the best tool. It was an experiment run with a fixed data set containing a number of components at various resolutions, and it was all done at the NCAR Wyoming Supercomputing Center. There were 6 tools used in the initial experiment, of which one was constructed a prototype just using MPI for Pi and PyNIO. And that, I should say, this is all NetCDF data, both the input and the output. So some of these other tools, the NetCDF operators is well known in the climate community, and it's a very versatile tool. But for I/O, it's just serial. And the other, there are a couple that use data parallel type operations, Pagoda, and the NC Reshapeer, the other prototype that has been developed at NCAR using Fortran and PIO. So just to explain data parallel versus task parallel, which is what the Pi Reshapeer essentially is. If it was data parallel, you'd be having multiple processes writing to the same file, which is more complicated, as opposed to each task parallel kind of situation where each process only writes to one file. Just to start off, this is kind of the scenario with the current tool, and so these were the test data sets. You can see there's quite a variety of sizes, and the highest resolution one, the POP, the parallel ocean model, has 3 terabytes of data, I think, more or less, and but interestingly contains the fewest number of variables, and actually that's somewhat significant later. So you can see that it was taking 14 hours to convert the POP1 from the time slice to time series. So here was the initial comparison, and now this is throughput, so that means the highest bars are doing the best job, the fastest job, and so it was surprising actually to everybody that this simple combination of PyNIO plus MPI for Pi did a significantly better job, and you can see it's quite a bit faster. And with the NC Reshaper, which was Fortran, and using a parallel I/O output was kind of the second best. So here's that same. Well, actually, this is now we've removed the. Well, just limited it to the best performing tools here, plus NCO as the base mark, and you can see that this is duration here, and we've reduced that 14 hours down to an hour and a half for the pot tenth of a degree grid, and actually since then we've made a few further improvements and in this case, it can be reduced even further. So those numbers are a little out of date now. So that's seeing that same data as throughput. So now the big bars indicate better. So what are the features of this Pi Reshaper, which is what we call the combination of MPI for Pi and PyNIO? Well, the input files are shared among the tasks. They all read the same input files. There's no contention there. And for output, there's one task per variable. There's one task per output file. It's simple MPI code, about as simple as you can get, really. There's no critical sections, there's no syncing, and it's admittedly designed for a specialized task, but it's already provided the inspiration for a new temporal averaging tool, kind of using the same principles. So it is extendable. So now I'd just like to I kind of promised in my abstract that I'd go through the code a little bit, so I'll do that here. And this is as it's been developed. I mean, this is not the original code, and it's also simplified. So basically, it's been developed into 4 different Python classes. The module, and so there's an init section which just does each process gets its rank, and it finds out how many processes are running, and that's little more than a hello world program, really. The other part that is important for the MPI communication is just partitioning this list of variables, and that's really all that has to happen. Is that it's provided a global list of all the variables, and it sorts them, and it does it by using a step, just regular Python syntax. It steps by the size of the variables, so it sort of takes one and then skips over to the next series of variables, and that's actually kind of important for the primitive data distribution that this does in its still developing state. So now here's the Reshaper, which actually does the work. Well, first it initializes a messenger, and then it reads all the input files and puts them in a list. It just opens the files, puts them in a list, and then it sorts the input files and classifies them by, well, first of all, it's not just the data variable itself, but there's also metadata, which I'm not really putting that in here. I'm not putting the stuff that creates the dimensions and the attributes in the netcdf file. or reads them from the original file. But there are a lot of actual subsidiary variables that are really metadata that have to go into every file. And so it classifies them by whether it's a variable that goes into every file or it's the main subject variable for this particular file. So then we do this partitioning, and that's where it's calling the messenger and getting its own little set of files to process. This is each process does this, and this is where the processes diverge. They just have a different list of variables, and so from there, it just opens the output file. And it reads the input file just to create the variable. It finds out, stuff about the input variable to create the output variable with the right type and the right number of dimensions. And then from there, it's just filling in the output file. So it's an unlimited dimension. So each time it does this, that output variable is growing. And that's basically it. So in honesty, it's MPI for Pi that makes this combination of things work. I mean, PyNIO is serial code by itself. It wouldn't do any better than, it would be comparable to the other serial tools. So, it's PyNIO, as far as reading NetCDF, is very comparable to NetCDF for Python. They're both derived from Conrad Hinson's scientific NetCDF module. So it actually made it easy to substitute NetCDF for Python into the code. And, I was interested in this for my own use. I just wanted to see, would NetCDF for Python do better or not? And so I did a little comparison since the test setup was already there. I took advantage of it, and we compared three different scenarios: writing out as NetCDF3, writing out as NetCDF4 Classic, and writing out as NetCDF4 Classic with compression level 1, which is actually significant compression, depending on the type of variable. If there's a lot, especially if there's a lot of fill values, like for ocean data, there's lots of fill values all over the Earth. It makes a lot of difference. So here's kind of what the results of this test was, and it's kind of interesting. I was really, actually, to be honest, afraid that NetCDF for Python would do better, but in fact, PyNIO performs pretty well, and especially in the NetCDF3 case, you can see that PyNIO is doing is quite a bit faster for large data. And also in the compressed case, there seems to be some differences. There are a few places where NetCDF for Python is faster, but and for a lot of these data sets, it's really a wash. So anyway, just interesting. So now, why PyNIO? It's as I said before, it's a NetCDF style interface to formats of interest, including NetCDF3, NetCDF4 Classic, and we will soon be supporting full NetCDF4. That's in development right now. We also support HDF and HDF EOS, GRIB, and that's We have, I would say, a pretty unique grid reader, and we also support shape files. So it's well supported. There's a lot of years of development that's been put in, and we also have pretty good support. We have a flexible interface to the mask array module, and we provide some extra value coordinates that are just appear as part of the file. If you're reading GRIB, you get coordinate data associated, that's kind of built by the tool, and you also get vector rotations. So for the next version, we're supporting the full NetCDF4 interface, and we also hope to make it a much easier install using Conda and also much more accessible. I know people have complained that they had to go to the ESG website and sign in and stuff to get the code, but now it will be possibly GitHub. We haven't fully decided that yet, but we probably will be going that direction. There's also a lot of improvements, format-specific improvements, and so we're going to release a new version pretty soon. I should say that PyNIO is just part of what we offer in Python. We also have Pingle, graphics code, graphics module, and it's basically the same graphics as you would get from NCL, if you're familiar with that. And it cooperates with other Python tools, and we hope to have soon a new Python analysis. We're hoping to make the NCL, I shouldn't say hoping, we're going to make the NCL analysis library available from Python. And that includes a lot of WRF functions that people are interested in. And so we are committed to the Python community. And so I'd like to say thanks to the people, my colleagues, John Dennis, who wrote the original prototype code, and Sherry Mickelson, who generated the test results right here in the room, Kevin Paul, also here in the room, who productized the Reshapeer, and Wei Wang, who's adding now the NetCDF4 capabilities PyNIO, and also, actually, I should say that that's going to include full HDF5 capabilities as well. So, and also I'd like to thank the MPI for Pi developers, who I don't know, but that's a great product, and the Python community. So thank you very much.